Chapter 4A, Example 5. So example 5 covers using z-scores to construct any percentage confidence interval. So we have been using the 68, 95, 99.7% rule to construct confidence intervals, but we could also go to a 90% confidence interval or any other percentage confidence we wanted. So using what we know that the 90% confidence interval must be between 1 and 2 standard deviations, since 90% is between 68%, which is 1 standard deviation away from the mean, and 95%, which is 2 standard deviations away from the mean. So a 99% confidence interval would then be between 2 and 3 standard deviations, since 99% is between 95%, 2 standard deviations, and 99.7%, 3 standard deviations. So here's a sketch of the 90% confidence interval. You can see here when we've got 90% in the middle, the z-score is between 1.65 and negative 1.65. And more precisely, we could say 1.645 for the z-score. For the z-score, we typically just write down the positive value because we're going to be adding and subtracting. Let me show you in StatCrunch how we can see this. So if we are in the normal calculator, I'm going to open a new normal calculator. So stat calculator is normal calculator. Notice by default it has 0 at the center. So if we go over to between and I want to know between which values is it 90%, over here in the equals I put in a 0.90 and make sure you're clicked on between. Our mean is at 0 and our standard deviation is 1. This is called the standard normal distribution. And we compute, here's that negative 1.65 and positive 1.65 that our image rounded to. So you can use 1.645, you can use 1.65. Your calculations will be close enough that it's no trouble. So if we think about 90% inside the interval, then what percent is outside the interval? Well, you've got 100% total area under the curve, so you've got 5% or 0.05 on each tail. So we say 0.10 or 10% is outside the interval. So here's the z-table with the exact z-scores. We see here's 90%, 1.645. We see 95% that we've been using 2 for is actually 1.96, and 99% is 2.576. So if you go back to StatCrunch and you want to check those values, just change this to equal 0.95, compute, there's that 1.96, and it's fine to keep using 2. Again, those values are close enough that we won't see major differences in our calculations. And if you want to see how far out is 99%, change that to 0.99. And here we go. This is what we rounded to 2.576. You could certainly use 2.5758. Then your results would be even more accurate. So using our formula for the confidence interval that starts here with our sample proportion p hat, we're going to use our z-score depending on what confidence level we are, and then our standard deviation. We want to calculate a 90% confidence interval for the proportion of statistics students. So in example 4, we calculated out the standard deviation, or the standard error because it came from sample data, so we call it the standard error. And that was 0.0267. Our sample proportion was 0.6469, and our z-score is going to be 1.645. So now when we calculate out the 90% confidence interval, the formula is our sample proportion, 0.6469, plus or minus, because we're going to have an upper bound and a lower bound, 1.645, because we want to be 90% confident, and that's between 1 and 2 standard deviations, times 0.0267. And then we multiply this and get 0.0439, and then we're going to add and subtract to find our upper bound and our lower bound. So when we subtract, the lower bound is 0.603, and when we add, the upper bound is 0.6908. So my statement can say that I am 90% sure about my methods that between 0.603 to 0.6908 proportion of students in stats at community colleges are also in English. So notice my language is not exactly the same language that I used in example 4, but it's communicating the same idea. Whether I say I'm 90% confident or I'm 90% sure about my methods, that's communicating the same idea. So you can use your own language as long as you're getting across the same points, that 90% is confidence in your methods, and that our estimate is for all students in community colleges. Now, to construct a 99% confidence interval, we shift to 2.576 here for our z-score. So notice our margin of error here, which is a 2.576 times the standard error, is bigger because we are going to have a wider interval with 99% confidence because we're going to be more confident in our values. So when we subtract, our lower bound is 0.5781. Looking back, we see, oh, that's lower than 90% confident, which is what we expect. And when we add, our upper bound is 0.7157, which is higher. So this is overall a wider interval. And we can say we are 99% confident in our methods that between 57.81% and 71.57% of students in stats at community colleges are also in English. So in question F, I say, why do you think the z-score for 95% is slightly different from 2? And that's because it's exactly 1.96, but it is okay to round to 2 standard deviations. So remember, you can always look up any z-score using the normal calculator, or you can go look at that z-table that we saw back on page 129. So you're not limited to these values, but I'd say 90% confidence, 95% confidence, and 99% confidence are about the most common calculations that we do. So now let's take a look at some data. So in StatCrunch, we're going to open up the file 2015 to 2016 NBA salaries. So in StatCrunch, to open a new file, you left click over here and then you can go to Explore, Data, and if I type in NBA salaries when I'm exploring, it should show up. You can see these are the most common things, so it looks like people have been doing fitness plan and modeling data here. So I'm going to type in NBA salaries. And here it is. And the owner is me, LMC Math 34. So if you're looking for a data file that I referenced, typically it's got me listed as the owner. All right, so we see Kobe Bryant was a top paid player in 2015. Remember, these are contracts that are negotiated years in advance, so you might be surprised that the MVPs aren't necessarily in the top 10. So that file includes all NBA players. So we want to think about what are the variables in that file. So if you check the headings, we've got rank, which is just the same as the row number, just enumerating the order. So our variables are really player, what position they play, what team they're on, and then the salary. So player, that's a categorical data, and that's unique. Each player has a unique name, so that would be a crazy pie chart or bar graph. There'd be a bar for each player. Position, let's go look at what a pie chart would look like for position. So we could do a pie chart for position, and we see the positions are pretty evenly spread. That's kind of interesting. It looks like there are more guards, maybe, 23% more than the other categories, but not surprising. The teams, that would be, if we did a pie chart, you can see that would be a little bit crazy because we've got many different teams. So you can see there's all the different teams in the pie chart. That wouldn't make too much sense. And then salaries are a quantitative variable there. So this is what we explained here. Player is categorical, team is categorical, position is categorical, and salary is quantitative. Rank is just enumerating the order, the row number, so that's not a variable in this case. It doesn't have much meaning or any meaning in terms of analyzing this data. So we're going to start with a sampling distribution like we did for the M&Ms. So we're going to go back to the applets and choose sampling distribution, and then we're going to choose salaries to make our data table. So we go applets, sampling distributions, and then from the data table, and we select the salary. And so up here is the histogram of all of the population salaries. So this is a population distribution. It's got a strong right tail. almost anytime you look at a salary distribution, you're going to have a few people making a lot of money, and you're going to have that same strong right tail relationship. So let's start by doing a sample size 2 and see what we get. We're not going to get the exact values that I got in the screenshot here because of variability in sampling. But let's check that out and see how our distribution compares to what I screenshotted in our packet. So we'll leave sample size at 2. You can see if we do it one time, it picks at random 2 salaries and plots both, calculates their average, and then what's getting graphed down here is the average or the mean of the sample size 2. So if we do it 1,000 times, we see this has got a pretty strong right skew. In fact, it looks awfully close to our population distribution. The thing that is not ever going to be down in the sampling distribution is we're not going to have Kobe Bryant out here in our sampling distribution, because it would be like they picked Kobe Bryant twice and averaged him with himself. So if you pick one Kobe Bryant and one other player from anywhere in the distribution, their average is going to be less than 25 million. So the sampling distribution isn't going to include that extreme value out here. And we can see that the mean of the sampling distribution is a tiny bit lower than the mean of the population distribution. And again, it's a little bit different than the values that I got in the screenshot just due to variability. So now let's adjust it to 3 times and 5 times and see if we can tell a pattern here. So if I do it to sample size 3, do it one time, notice now it's pulling out 3 data values and plotting them. We can watch it 5 times in a row. If you do the simulation on your StatCrunch, it's not going to be the exact same points picked out. But if you do it 1,000 times, you should get roughly the shape distribution. So this is still right tail or right skew distribution, but there's no outliers out here, because imagine you're pulling out 3 salaries and averaging them. Not all 3 of those salaries are going to be Kobe Bryant. So you're going to lose, when you're averaging 3 samples, you're going to lose the right tail part of this. Let's check what happens if we change to sample size 5. We do it 5 times, we can watch the simulation pulling down 5 values. And then what if we do it 1,000 times? So again, we are losing even more of that right tail. Should we check what happens if we do sample size 10? We'll just do that 1,000 times. Now it's getting closer to normal. We're losing this right tail out here. And look at the mean. It's pretty spot on, close to the population mean, but the standard deviation is shrinking. Let's try sample size 15 and do that 1,000 times. Again, the standard deviation has shrunk for the sample means, but the population mean and the sample mean is still pretty close. So they're still centered at the same mean. That's the green bar here, but we're getting closer to normal. So let's see, what if we do sample size 20? This gets really normal. You want to try sample size 30. We see our standard deviation is much smaller because our sample means graph is more compressed. The mean is still about the same place, but it's closer to normal. And then if we go all the way up to, say, 40, it's still looking pretty normal. And the standard deviation has shrunk even more because this is pulling 40 values out of here and averaging them. So the trend we see is that as the sample size increases, the sample means distribution graph is roughly normal and narrows in width, right? It gets more compressed when you have larger samples. Here's some screenshots showing just what we did together. And we see down here when we went all the way up to sample size 30, it's much narrower and the standard deviation is much smaller than when we had sample size 2 up here. And the reason is because, right, if you're taking sample size 30, you're not going to have 30 Kobe Bryants and you're going to lose the right tail part of your graph when you're averaging 30 values. So based on the results of the sampling distribution and our estimated values, we can construct a 95% confidence interval. So I'm using values from the screenshot. You could use values from your calculations. They would be close but slightly different due to just variety and sampling. So we want 95%, so I use just 2 here. You could use 1.96. So we start with our sample mean. That's this 5.1099 from my screenshot here. And then we're going to add and subtract 2 times the sample standard deviation. And so we got a lower bound of 3.2267 and an upper bound of 6.9931. So I ran out of space, so up here is my interpretation. So with 95% confidence in our methods, we predict the true mean MBA salary is somewhere between 3.2267 million to 6.9931 million. So now in StatCrunch, we can go find the actual population mean and population standard deviation that's unadjusted. You can see this in 2 ways. You can see it up here in the population graph, or if you want to, you can go Stat, Summary Stats, Columns, and choose Salary, and then you want the mean and the standard deviation. So click on both of those. And you can see these are just the same values as they're showing us here. Oh, this is a little bit different because I think they divide it by n minus 1. And so that's just a difference in the formula when you're sampling. In this case, it's so close that if we go to 1 decimal place, it's the same 5.2 for our standard deviation. So now we're going to use these values to calculate sigma divided by square root of 30. And the reason we're dividing by the square root of 30 is because we went up to a sample size of 30 in our last screenshot here. This is when n was 30, and our sample standard deviation is 0.9416. So what happens if we do that? If we take sigma, our population standard deviation, divided by square root of 30, that's 5.2152 divided by square root of 30, which works out to be roughly 0.95. So, hey, wait a minute, that's really close to what we got here for the sample mean standard deviation when our sample size is 30. So when we're sampling, we use this formula, sigma divided by the square root of however big our sample is, to figure out how that standard deviation is getting compressed. So when we sample and graph the sample means, we calculate the shrunken or compressed standard deviation by calculating this formula, sigma, the population standard deviation, divided by the square root of n, and you can use capital N or lowercase n for the number of samples. So we've observed 2 important facts in this activity. So the standard deviation of the sampling distribution is smaller than the population standard deviation. In general, when a population has a mean mu and standard deviation of sigma, the distribution of all possible sample means from the population is still going to have mean and mu. The mean doesn't change, but the standard deviation shrinks to be sigma divided by square root of n. If n gets to be larger samples, the square root of n is going to be larger. Sigma divided by square root of n is going to be smaller. So note here, n is what we call the sample size, or the number of independent observations from the population. We want to make clear that they're independent. In this case, we were using random draws to ensure that things were independent. You wouldn't want to just count people as they walked into a room because that would be problematic and could have bias. If a sample consists of at least 30 independent observations, in this case it was random samples, right? And the data are not strongly skewed, then the distribution of the sample means is well approximated by a normal model. And that's just what we saw if we look back at our applet here. When we had more than 40, we got a normal model down here for the sample means, even though the population distribution here had a right tail or a right skew. So these results are what are known as the central limit theorem, or we'll say CLT for short. And our open interest textbook talks about this more in depth on section 4.4, so make sure you read pages 194 to 196 for the in-depth explanation.